Alright guys, hopefully in this video the audio will be a lot clearer. Once again, apologies about the first video, the audio not being very clear. Okay, so what we're going to have a look at here is a few worked examples of calculating limits. Okay, the first method here I'm going to have a look at is an algebraic one. So quite often the question will be given in this format here. You're simply given a function, asked to find the limit. So one thing you could do is you could graph this and have a look at the limit using a graphical approach. But in some circumstances like this one here, what you can do is you can simplify the algebraic, what you're given algebraically here, and quite often the simplification will involve factorization and cancelling of common factors. So this top quadratic here can actually be factorized into 2x plus 1 and x minus 5. And the bottom line you might recognize as the difference of two squares. That can be factorized into x plus 5 and x minus 5, and hopefully you can see that there's a common factor there. Notice that in my working I am carrying this limit notation down. It doesn't disappear and reappear like Harry Potter. So what we've ended up with is this simplified fraction here. Now why can we basically, what do we do now at this stage? Well, what we're going to do now is we're simply going to substitute the 5 in. And why can we do that? Because this fraction here will not be undefined. And why couldn't we do that at the beginning? Because if you put 5 into the function at the beginning, the bottom line would have turned out to be 0, and you would have ended up with that number over 0 undefined situation. So you never calculate a limit by substituting something into the function which is going to make it undefined. Right, so what do we do at this stage? Well, we simply now substitute the 5 in. So that means 2 times 5 plus 1, which will give us 11. Okay, and 5 plus 5 on the bottom, which will give us 11 over 10. Okay, which is fine, or 1 1/10 or 1.1. Okay, so algebraic method, key ideas, especially when you got a fraction here, look to factorize, cancel common factors. When the fraction you end up with here, this thing here, is no longer going to be undefined, then you can substitute whatever this value is into the function. Okay, and that will give you some value which will be the value of the limit. Okay, let's move on to the second example. Okay, a table of values. Okay, so what do I mean by that? Well, what we're going to do is we're going to get a table of values around x equals 3. So how do we do that? Well, one method, you could use your graphics calculator for that. Okay, what I'm going to do is I'm going to actually use Graphmatica for this. So I'm going to clear what I've currently got here. Okay, and I'm going to type in that function. So y equals, and then on the top line we've got x squared minus 6x plus 9. Let's close that bracket off, and then on the bottom, also in a pair of brackets, okay, we're going to go x minus 3. Okay, and obviously we've got a graph here, but one of the things that you can also use is a table of values. Let me just try and find out where that is. Tools, where is it? Point tables, that's the one under view. Okay, so what we're going to do here is we're going to set up a few values that will actually produce more than just this what we've got here. So I'm just going to pause the video. Okay, so just back here again. So if we're going to get these table of values showing something sensible in Graphmatica, under options you need to go to settings, then go to point tables, and then say okay, so what steps do we want to basically show on our table? The x values, they should go up by how much? Okay, so what we're going to do is we're going to put in here 0.1. Click OK, and then I'm going to view, sorry, not view, once again, where where's that? Sorry, under view, so there's point tables. Okay, so now I'm going to scroll down to where x is approaching 3. Now we can see that it's undefined when x equals 3, and from the table of values, the x values approaching from the left hand side, as x gets closer and closer to 3, the y values seem to be decreasing down, getting closer to 0. And if we look at the graph, we can certainly confirm that that is true. And from the other direction, coming down towards x equals 3, okay, we can see that the y values are also decreasing, okay, getting closer to 0. So what does that mean? It means that if we look at that table of values and simply record well from that, okay, we can say that the limit is equal to 0. Now the thing about a table of values, of course, is that they can be a bit messy and time consuming to calculate, especially manually. So if I was given a choice, I'd simply go for the graphical method. And let's have a look at another example of that here. This is actually a question taken from your workbook number 15 on page 79. I'll simply regraph that here in Graphmatica. Okay, and it's an opportunity to have a look at an idea that we haven't discussed before, and that is this idea of what's called a limit to infinity. So we've got this infinity symbol here. Okay, and what does that mean? What it's asking you is saying, well, what's happening to the function when you make x extremely large? Okay, that's all that's asking. And if we look at the graph, if I make x extremely large, okay, what's happening to the y values? Well, they seem to be decreasing. And if we kept on going and going and going across this way, the y values are getting closer and closer to 0. So that's simply what the limit is. So the limit to infinity is simply asking you, in this case, what happens to the function if x is made very large? So let's say very, very, very large. What's happening to the y values? Well, they're getting smaller and smaller, approaching 0. Okay, let's have a look at the next one. Limit as x approaches 2. So what's happening to the function around 2 here? Well, from this side, looks like we're getting down towards 1 here. And from the other side, we're also getting closer to the same value. So that means there is a limit and it equals 1. Okay, what about when x equals, or not equals, around a half here? Well, looks like a half's here, another undefined point here. Okay, but from this direction, the y values are getting closer to -2, and from this direction, they're also getting closer to -2. So that's the limit. Okay, here's another infinity one, but this time there's a minus sign in front of it. What does that mean? Well, it's simply asking you what is happening to the function when you make x extremely small, heading off towards negative infinity. Well, I think we can see that the function is negative, but the y values are negative, but they're getting closer and closer to 0 again. Okay, and so the limit as x approaches negative infinity. Okay, what's happening to the y values? They're getting closer and closer to 0. Okay, now this here is not a limit. It's not asking you for a limit, but it's the kind of question you do see in your book, so I thought I'd cover one here. What is this asking? It's saying, well, if x is 3/4, 0.75, what's the value of the function? So let's go back to our graph here and say, right, if x is, well, there's 1. Okay, in fact, I should have corrected this. This is wrong here. This should have been 1.75. 1.75? No, 1.5. My apologies. Let's correct that. What's happening to the function when x is 1.5? Well, what is the value of the function when x equals 1.5? That's what this is asking here, and the value is 2. So this is not a limit, it's actually asking you what is the value of the function when the x equals 1.5, and we can simply read that off the graph, or if we had a function we could simply substitute the 1.5 into it. Okay, when is the function undefined? Well, it's undefined when we don't have values that we can say x is exactly equal to this, or the y value, sorry, is exactly equal to something. Okay, well, we can see that when x equals 2, we've got a hollow dot there, so the function is undefined when x equals 2. There's another value that we saw before, and that was when x was equal to 0.5. Okay, we've got another hollow dot here. Okay, so 0.5, the function's undefined, but there's another value. Notice we've got this vertical asymptote, it's called, where the function, okay, breaks left and right parts to it. So when x equals 1, we don't have a defined y value either. So that would be another value when the function is undefined. Notice we list the x values here. Okay, we'll have a look at one more example in a minute. Just pause this to get it ready. Okay, so this millionaire theory one, what's this about? Well, in this case, what we're asked to do is to find the limit as x tends to infinity. In other words, as x becomes extremely large, what is happening to the function? Well, sure, we could graph this. That is definitely one way, but here's another alternative. Okay, to calculate this, what we can do is we can say, well, if I make x extremely large, what happens? Okay, so if I, for example, were to look at making x equal to 100, I know that's not extremely large. Well, parts of it are, because if you try and calculate this, well, your calculator's going to freak out about this, because it won't be able to hold 3 to the power of 100. I don't think it will anyway. But what you've essentially got is a relatively small number on top, relatively speaking, because this bottom number is ginormous. And when you divide a small number by an enormous number, well, that gets just closer to 0. Okay, so if we, for example, looked at 1 over 1 million, enough zeros there? Yeah, I do. Well, that's going to be 0.000001, very, very close to 0. And this is actually quite a nice limit to remember. Oops, get rid of that. In fact, I won't just make that 1 on top, I'll make it a number, any number. Come on, pen, get going. N over x, okay, is going to equal 0, where n is a number, and this number here tends off to infinity. Okay, this is going to equal 0, this limit. So what does that mean for this situation? Well, what we've got is we've got basically a number, if we actually substitute infinity in here, and 3 to the power of infinity is ginormously larger in comparison to this one. So once again, okay, using the same idea as we just talked about, this limit is equal to 0. So the millionaire theory basically means substitute a really large number into top and bottom, and then look at what's happening to the function. Okay, so that's the millionaire theory one. Alright folks, that'll do in terms of the videos. There'll be questions for you guys to have a go at from your workbook based on this.